Welcome back. We're going to talk about the Matroid intersection polytope in two lectures. So this is the first lecture. We've already seen an algorithm that was very reminiscent of alternating paths and augmenting paths for finding the maximum cardinality common independent set. And we've seen the other basic result on Matroid intersection, which was the Matroid intersection theorem, which is essentially this duality result. We didn't prove it as a duality result, but we can use these results to revisit that. So before we get into that, let's talk about exactly what we want to show. The setting is the usual one. We have two Matroids on a common ground set, M1 and M2. And what we're interested in now is the polytope that I will denote by P of M1 intersection M2. And what this means is that we're going to define this the way that we've usually defined polytopes of combinatorial structures. Let's look at exactly everything that's in there and take the convex hull. So it is the convex hull of the incidence vector of every common independent set. So chi, the indicator function chi I, for I, any element of this intersection. In other words, anything that is independent in both Matroid 1 and Matroid 2. And the main result that we're going to prove in these two lectures is that this polytope is in fact equal to this intersection. And this is useful, and it immediately gets us a polyhedral characterization of this polytope. In other words, a characterization in terms of inequalities, because we've already seen what is such a description for individually the independent set polytope. So recall that we showed in a previous lecture that for any Matroid M, we denoted it differently then. We called it the independent set because there was only one Matroid and it was understood, but I think this notation is clear in this, is more clear in this context. Recall that we showed that this is the intersection of the positive orthant and also all of the constraints that x of f is less than or equal to r of f for all exponentially many subsets of the ground set, where again R is the rank function of M. So in particular, this theorem then implies that we have that the polytope of Matroid intersection, being the intersection of the individual polytopes, is equal to the intersection of the non-negative orthant with the constraints x of f bounded by r1 of f and r2 of f. X of f bounded by r2 of f, or if you like, the minimum of r1 and r2 of f. Again, for all exponentially many subsets of the ground set. The other nice thing that this immediately shows us is that if you have an oracle for either M1 or M2, then you have an oracle for P of M1 intersection M2. That's what this intersection result tells us. So if you have a separation oracle for P of M1 and separately a separation oracle for P of M2, then you have a separation oracle for P of M1 intersection M2. In other words, we can easily optimize if we can optimize over one of them individually. Okay, so we're going to build up machinery towards this result. So first, let me define what tight constraints means we've seen this word tight constraints before, but I want it to mean something specific in this context of the Matroid problem. So let me write it as a definition because we'll be using it a lot. So let's let X belong to the polytope of a Matroid, the independent set polytope. Whenever I write P of M or I say the polytope of a Matroid, I'm always talking about the independent set polytope. Then a subset of the ground set is called tight if X of U is equal to R of U. So this is really not saying anything different than what we've talked about before. It's what are the tight constraints. The constraints are indexed by subsets. I just want to be able to talk about a set being tight. So that's really, I'm just going to be using that definition in a more compact way, and that's why I'm writing this as a definition. And it turns out, this won't surprise us, it turns out it shouldn't surprise us, because if we think back to the lecture where we where we gave the polyhedral characterization for the independent set polytope, we saw that we could take the support to be a laminar family. And the support is exactly going to be is very related to these sets, as we're going to see. Though this doesn't mean though they're not synonymous. The first lemma that we're going to prove says the following: if X is in the independent set polytope of a Matroid, and if I have two subsets of my ground set that are tight, then so is the intersection of S and T and the union of S and T. And so are S intersection T and S union T. So in other words, if these are subsets of my ground set, then if S and T are tight, then so is the intersection, and so is the union. And this really follows very simply. R of S union T plus R of S intersection T, just by the fact that X is feasible, they're each individually greater than or equal to X of S union T plus X of S intersection T. Again, if X is feasible, then X of any set U is less than or equal to R of U, and therefore individually these two terms are on the left bound the two terms on the right. But remember, what X of U is just the sum of Xi for all elements of U. So this, of course, is exactly equal to, just by linearity, X of S plus X of T, by linearity of the definition of what X of S means. And now, since S and T are tight by assumption of the lemma, this must equal R of S plus R of T. And then, by submodularity of the rank function, this is greater than or equal to R of S intersection T plus R of, let me stay consistent in the order that I write things in, R of S union T plus R of S intersection T. And this implies that I must have equality throughout. And therefore, S union T and S intersection T are also tight. The next and one of the two main important lemmas that we need in order to prove this Matroid intersection, the theorem about the Matroid intersection polytope, is the following lemma, which talks about nested sets with respect to a single matroid. So let's, again, let X be an element of the independent set polytope of a matroid. And let script C be a collection of subsets that are nested and tight. Now, whenever you have a nested set of sets, this is called a chain. So this is part of the jargon. So let script C be an inclusion-wise maximal chain of tight sets. And again, chain means that these are just a collection of nested sets. And since they're tight, this is just saying that X of Ci is equal to R of Ci. So this is the setting of the lemma. And then the lemma guarantees the following. It says that in this case, any other subset of the ground set that is tight must satisfy the property that its indicator vector is in the span of the indicator vectors of elements in this chain. And again, in this case, we're using the span in the ordinary linear algebra sense, not in the more general matroid sense. So the lemma says that in this case, any set T that is again tight, and again tight is with respect to X, must satisfy that chi T is an element of the span of chi C, where C is some element of this inclusion-wise maximal chain of tight sets. Okay, so let's see how this goes. So first, let's suppose not, in order to come to a contradiction. And if not, then there exists some set T that's tight yet violates this constraint. And let's now ask, what is this set T? So one option is if T is not contained in CK. CK is this final is the largest set in the chain. So if TK is outside that, then I'm going to immediately just use the previous lemma, and we're going to be using that previous lemma was very simple, but it's going to be very useful for us. So if T was not contained in that, we're going to violate this inclusion-wise maximality because we're going to construct a containing set of CK that is also tight, just using the fact that tight sets are closed under intersection and union. Let's write that out. So if T is not a subset of CK, then let's just let C hat equal whatever that union is, and then again, since union is preserves tightness, then the previous lemma might as well name them. Let's call this lemma 1, and let's call this lemma 2. Then the previous lemma, which we've now called lemma 1, says that C hat is tight, and this violates our inclusion-wise maximality because we have this property. So that can't be. Okay, so we've ruled out that possibility. So next, let's suppose that T is a subset of the largest CK. So it has to be like that. And let's draw what our nested subset looks like. So this is, the smallest one is C1, C2, etc. So these in between, I'm going to call the increment sets. So in this example, if this is, let's try it a little bigger. If this is C1, and this is C2, and this is C3, and this is C4, then the increment sets are just C4 minus C3. This would be C3 minus C2, and so on. So we ask, what we know T is contained in CK. That would be C4 in this example. Then T could be the union of some of these increment sets. And if it's not that, then it has to partition one of these increment sets into two. So, so first, let's suppose that T is in fact the union of these entire increment sets. So you know we know T is somewhere here. Right? This is T, and this is an example where it is not contained in the it is not equal to the union of some increment sets. So in other words, we know that T is contained in the union of these increment sets. Let's first assume that it's not as the picture is drawn, and first suppose that T is a union of several of these increment sets. So in other words, it might be C2 minus C1 and C4 minus C3, something like that. So in other words, let's suppose that T is the union of Cj plus 1 minus Cj for some collection of these. But in that case, we see that, again, we come to a contradiction right away because we find that this indicator function of the set T is, of course, equal to the sum of Cj plus 1 minus Cj for j and j. Again, because see, I don't have containment. I have it is exactly equal. But again, because of the nesting property, I can express the indicator function of the difference as the difference of the indicator functions. If the sets weren't nested, I wouldn't be able to write this. So this is equal to the sum of chi of Cj plus 1 minus chi of Cj for j and j. But I've exactly shown that chi t is in the span of xc. And so this is an element of the span of chi c, which contradicts, which is what we want to show. Okay, so we have one final case left to consider. I guess I've called this lemma 2, just to be consistent here. The final case that we have to consider is that the picture is as we drew here. So therefore, the only possible remaining case is that there exists some j with t intersect Cj minus Cj minus 1 is a proper subset of Cj minus Cj minus 1. In other words, T does not fully contain one of these increment sets. And again, this is the picture from the previous page. This is this situation. So again, now what we're going to do is use lemma 1, and we're going to contradict the maximality. Again, we can use lemma 1 to contradict the maximality of C. And we're going to do this as follows. Let C hat be the set that's T intersection Cj union Cj minus 1. You can just see it from this picture. So it'll be this set, and you can see exactly what's going to happen. The lemma guarantees that this is tight, and it also guarantees that this set is distinct. It is a proper superset of Cj minus 1. It is a proper subset of Cj. So it's again tight, and Cj minus 1 is a proper subset of the C hat, which is a proper subset of Cj. So this is again a contradiction. So what we've shown a result about this is really an intermediate result that tells us about the span of certain sets. In the next lecture, we're going to extend this. We're going to use this result to look at chains in both of the matroids. And then finally, this will have given us the machinery to prove the main theorem by induction by using contraction and deletion. So we're going to pick that up in the next lecture.